All right, so we talk about chapter 23, sorting, CSC200. The date is October 2nd. All right, now we are talking about how would you design and implement different sorts. So we look at insertion sort, bubble sort, merge sort, quicksort, a binary heap sort. Now when we talk about, we have something we call like hatching. We talk about bucket. Okay, so we're gonna look at that and radix. And lastly, said analyze external sort for files that have a large amount of data. I think last time did I talk about insertion sort? No, never. All right. So let me ask you first then. If I want you to sort the numbers, how would you sort this number? Huh? Let me hide the code. Say one way, use two loops. So what's the first loop do?
First loop goes from beginning of the index to the end.
Compare. You said compare the first one to the second one, and compare the first one to the third one to see if it's less than, like one is less than, right? So what do? You have to swap it, right? That's one loop, correct? And you're repeating the step with the remainders. By say 9, now it's going to be the key that you want to compare to 5. Let's start to swap, right? And then you take 5 to compare, now you have 4, you swap again, right? And then that's it, and then that's done with the second loop. So meaning you need 2 loops. Let's think, is it nested loop or not? So find the smallest, swap, and keep repeating itself, right? Yeah, because so the smallest actually should be an inner loop, right? In this case, because like in the scenario that I show you here, 9 and 5, you swap 5 and 9, but it's not done yet. It's still an inner loop until the end, so that's why you keep comparing to the third one. Then you swap 4 and 5, right? That makes sense? And then that's pretty much an inner loop until the end of the list, right? And then the outer loop pretty much just, okay, we start to the smaller list and getting smaller and smaller, right? So the outer loop pretty much just try to loop through the whole list. This inner loop pretty much just try to compare and swap. So what's efficiency? N square, right? Nested loop N square. Even the inner loop has the amount reducing, but we said we look at the big O, right? That means we just look at N squared. We don't care about efficiencies, even if it's divided by 2 or reduce this time, right? We just say it's N squared. We drop the coefficient, and we call multiplication, or the multiplicand terms we drop, and the another term that when you add, we drop that, right? Because that's just so small, right? All right, now first this is called an insertion. That's called a technique that you want to sort by insertion sort. So let's look at an image, right? So initially sorted contained the first element. Insert 9 into the sublist. The insertion sort, the technique that we mentioned earlier, is different than insertion sort, right? But I want to look at how the insertion sort works. There are many ways to sort. We try to find a location of 9 by comparing, right? So we see 9 is less than 5, so 9 should not be here. So swap. And then we compare, and we see that 5, 4 should not be there, right? 5, then we swap again, right? And now we start to get to the 9 again, right? 9 is less than 8, then we swap. And then we look at 9 and 1, right? And we see 9 should be right there, and 1 should be the first one, then we swap, right? So it's keep finding it and keep swapping until you get the location for it, right? Then this is in order now. But the way it does is it's just actually do inserting. It keep inserting until it's found its location. So this is called insertion sort. So what's the efficiency? That's a good question, right? So let's look at how we understand a little bit how it works, but how we're going to implement it, right? So let's look at, we use an array. This is in the list. So step 1, we say save 4 to the temp current element, right? Step 2, move list 2 to list 3. So list 2 is 9. That's why 4 has to be saved, because it's going to replace, right? Pretty much this is a logic to swap, right? And next, move list 1 to list 2, right? Since we see that 4 is actually less than 5, so we move 5 to list 2. And step 4, just move 4, which is in the temp variables, into 1, because we know that it's going to be greater than 2. So that's pretty much just it keep finding the location to insert, right? So let's look at how we implement it in the code. So we see first, we start from index equals to 1, and as long as it's list.length. So why we start from 1? Because we're looking at if you look through the list here, we're actually looking at here 9, right? That's index 1. So we didn't start from 0, right? And now from index 1, we compare to, pretty much we want to loop through the whole list, right? List.length. And then we assume the first value we want to put in the current element, like to hold. And then we start to loop to compare, right? So we said k equals to I minus 1, which is what? Like index 1 is 1. Now we compare to index 0, right? Start from 0. As long as greater than 0. We talk about index, right? Index is greater than 0 and the value is greater than the current element. So whenever the value is greater than, then we need to do swap. And this is the logic to swap, right? So meaning that if it happened to be not greater than, we're not going to have to swap. So it's pretty much just keep comparing and then insert, right? Or technically this is a logic to insert, yeah. So by looking at this, what's efficiency then? It's nested loop, right? N square, right? So let's look at another sorting technique we call bubble sort. So let's look at the list again. So bubble sort pretty much is try to bubble, like if you actually change this into vertical, okay, this is horizontal, right? So it's try to bubble up the values. Like starting from 2 and 9, we see that 9 is in the right location. We compare 9 and 5. It seems like 9 has to be bubble up, right? Or bubble to the right. Let's say if you look at vertically, it's bubble up. So this is bubble to right. And then now we compare 9 and 4. We see that you have to bubble it up. Bubble. 9 and 8, bubble again. 9 and 1 is bubble again. Alright, so we're done with that. Now we start to look at a smaller list, which is 2 and 5, which is correct. We look at 5 and 4. We see 5 has to bubble up. And 5 and 8 has to bubble up again. And then 8 and 9, which is the right location, we stop. Now we look at 2, 4, 5, 1. Right? So we start to look at 2 and 4, which is okay. 4 and 5 also okay. Now 1 and 5, nope. So we have to bubble 5 up, right? Now we look at smaller list again, which is 2, 4, 1. 2, 4 is okay, but 1 is not. So we bubble 4 up. And then again, 2 and 1. So we have 2 up. Now the list is in order. That's another way to sort. So by looking at this, how would you do this? So we pretty much just need to loop again, right? So the first loop pretty much just going to iterate. Like again, we start from 1 because 9, right? K equals to 1 and to the length. Pretty much just iterate from 1 to the side of the list. And then the inner loop itself is the one who start to compare, right? Compare like 2 and 9, all those blue, right? And do the bubble up, or we call swap here. And then like the inner loop is the one who do all the blues here until it's done. And then the outer loop just reduce the list to be a smaller list, right? So k equals to 1. Now we start to look at the smaller list until it's done. So this is pretty much what's the efficiency of this. Nested loop is going to be n squared again, correct? So this talk about if no swap takes place in the past, there's no need to perform the next pass. Because our elements are already sorted, that's true. So like you can see, for example, it said no swap, right? So like if no swap takes place in the past, like if you do first pass, like you see this keeps swapping. Because 5 and 9, right? 9 and 8 has to swap. But think about if there's no if there's no swap at all, then that means it's already sorted. Is that true? Let's say if I have 1, 2, 3, 4, 5, I compare 1 and 2, and then I do compare 2 and 3, and 3 and 4, 4 and 5, no swap at all. Because the list is sorted. The only time that is swapped because like 1, 2, 3, 5, 4. Then the first pass has to swap because you bubble 5 up. Meaning you can revise your algorithms here. If the list is already sorted, you don't need to loop again. There's a next pass equal to false. Now, in the first pass, this is merged to first pass. If we see the next pass needed, that's true. Otherwise, it will never get in here. So first we set need next pass equal to true. See that? And we did and we need next pass or not. The first time is going to be true, but we default to false. And if it never get in there to swap, then this is done. Correct? Only first pass is done. So, I mean, in the case of sorted list and you try to sort again, then the efficiency is going to be just n. But if you don't do this, algorithms need next pass is going to be n squared, same. Correct? This is just test the bubble sort. So next, Mergesort. All right, so what's Mergesort? So let's look at, I have unsorted list. So now let's think about, if I sort this list, how long it's going to take? N squared, right? Based on what we have learned so far. What we said, if I split this list in half, half and half, how long it's going to take? For each list, I'm going to note down, right? So the first one we said is going to be n squared, right? Now let's talk about this guy. The left one is going to take n squared. Are we all agree? We already learned that, right? To sort, correct? And the second one is going to be n squared too. Is that correct? Even the list is smaller, right? So when we add them up, what do we get? 2 n square. So assuming that n is 100, if I say n equals to 100, what do you get from here? Correct? About 10,000, right? If n equals to 100. Now can you tell me what you get from this one?
20,000.
20,000? But we don't do that, right? It's gonna be, actually, I did it wrong a little bit here. It has to be this, right? Because we divide in half, right? N divided by half square, correct? So we have a 2n divided by half square. Is that correct? So in this case, what do you get? N equals to 100, 5,000. Is that right? Because 100 divided by 2, you get 50. 50 square, 2,500 times 2, 5,000. All right, so if you keep doing this, if I split again and again and again, this number will be reduced half to 2,500 to, correct? It will reduce in half and half and half and half. Do you agree? If we keep doing this, right? Meaning that if you split the list and sort them as a smaller portion, and then you merge it back at the end, like this one, right? Look, it said, okay, 2 and 9, 2, 9, 5, 4, right? We split again, and we see, okay, 2 is in the right location, but 5 and 4, when you merge, is the time it's look for the location, right? We see 5 and 4, 4 should be on the left, right? And then you find the location to merge again, and you see it has to be 4, 5 should be between 2 and 9, right? So same 8, 1 should be 1, 8 when you start to merge 6, 7. Now let's think about, we get the algorithms to split. So we know that to split is going to take about log n then, because half instead of n, correct? How about to merge? Merging is you physically has to go through all of them and find the right location, right? 1 and 8, 6, 7. Now we see 6 is between 1 and 8, right? We're merging by inserting it in between. And now we see 2, 4, 5. And when you merge, you pretty much just have to go like, okay, look at 2 and 1, right? You start to compare, right? And we see that, hey, 1 should go before, right? Then we take 2, and we also look at the next one. Should it go between 1 and 6? No. Like, we can see 2, 4, 5 should go between 1 and 6. Then we just say 1, 2, 4, 5. Right, and then we look at 6 and 7 and 8 and try to compare back. 5 and 9. So we see that 6, 7, and 8 should go between 5 and 9 we insert. So how we going to implement this type of merging? We're going to have to use compare. We're going to have to go to index, right? This is an array. So we're going to go to the first index of the one to the left, and the first index of the one to the right. Compare the values. If we found it, then we pretty much just going to create a new array. So this is a new set of array, and we move that into a new array right away, one by one. And we keep doing that. Pretty much just have to iterate to the whole list. So how many would one loop enough to do that? No? Okay, let's look at how we're implementing then. So we create a method named Mergesort. So we're going to make sure that the length is greater than 1. Otherwise, we pretty much don't have to do the whole thing. Because if the length is 0, that means the resort is only one element. Now we're going to divide it. We create a new array, right? Initialize the size first half, right? This one using array copy. List forms. Pretty much just copy the first half. This is how you split, right? Right. 0 to the length divided by 2, and you put into first half. So now if you want to know how array copy works, you pretty much just need to look up on the system Java doc. So it's going to tell you the parameter. So the object source position. So we can see we start from 0, right? And the object is the list. And this is the destination object. Destination object is the first half. And then the destination position from 0 until the end, right? Which is half of that. So technically, this one pretty much just copy the first half of the list. And you can see this out thing will efficiency for this is just 1 constant time. Now it depends on Mergesort, right? So let's look at that is called Mergesort first half. So it's actually called itself. So this is called recursion, right? So itself is going to do the same. It's going to split in the first half again and again and again, right? Until that's why we have the base case. That's the reason why we have to do the list, because it is recursion, right? So when it's greater than 1, we will do until it's just 1. That means individual itself. So this is the same for second half. Now we're interested to look at merge. Like I said, we're gonna have 3 lists: the first half, second half, and the list itself, which is the whole size of the list, the new list. Or it's actually can just get the same list because you're gonna replace it anyway. Now let's look at how to merge. So we initialize current 1, 2, and 3 to represent the current index for list. List 1 is the first list, list 2 is the second list, and temp is the final list. That is sorted list. So we're going to iterate. So we're going to iterate while the index less than the list 1.length. Pretty much this is the first half, and the same, this is the second half index. And we start to compare. Let's say you start to compare one by one the value of the list 1 and list 2. If it happens to be less, then you pretty much just move it into the list itself, right? The list itself. What do you move? If it's less, then you move the contents of first half. If it's greater than, you move the contents of second half. That's how you merge. And now we look at this is for in the case of it's even, right? If the list is even, like if the list size 10, first and second is going to be the same size, 5 and 5. But what happens if the list is odd, right? So that's why we have to take care of this too. One second. Oh no, this is happen to be, this is we compare, yeah, in the case of the index less than the length for both of them. The current index that we start to be 0 because we're going to increment them, right? By plus plus. And eventually is it possible that, because if you think about, it's going to be always going to be less than, right? But in this case, both of them are less than. I was thinking, is it possible is that it's going to be in the situation that one of them is going to be greater than the length? It will never do, right? So this is going to be just one of them and one of them. Pretty much, you can look at this as the rest of the list that you have to put in the temp. You guys can see that? Because this is, you start to compare, you insert them in the case of both of them. But what happened when you reach to one list is done, you still have the remainder of the other list. In the case that when you split in half, let's say if it's odd and even, that's going to be 1. Because in that case, if we never reach this, right? Because this is an operator, so we have to take care of this. Yeah, technically odd and even is correct then. That's only a situation. And then it's going to compare if it's going to be, because it could be the list 1 or the first half, right? Or the second half that is going to be greater. That's going to do this one. Remainder is going to go. By looking at this, maybe you don't really need a loop too. Because if you split correctly, it should be just one different. But you use this while, like, because you have to say either if, yeah, while if. I think if should work too. Anyway, it's going to be just constant time by looking at this. So meaning that this is going to be what, n, right? And this is going to be 1 and 1, right? And this, you're going to add them. Even this is n, you can add, it's going to be 3n, right? Meaning that n, right? So what's the efficiency of the merge sort then? Merge took n. Sort is always in half. It's going to be log n. We talk about that, right? We talk about log n for split, right? And merge back. This is merge sort. So merge is going to be n. So merge sort is going to be n log n, right? Because both of them has to multiply. Right? Because merge sort always calls merge, and you keep call merge sort over and over again. Like it's nested inside. So it's multiplying. So any question on merge sort? This is just showing you again how to merge. When after you compare, you put 1, 2, 4, 5. It's better now, right? It's better than bubble sort and insertion sort because the efficiency is in log n. But I didn't say it's the most. Okay. Yeah, this is how we evaluating it again, right? Merge time, so it's in log n. Sort time is in half. So another one we have is called Quicksort. This says select an element called a pivot. Divides the array into two parts so that all the elements in the first part are less than or equals to the pivot. And all the elements in the second part are greater than the pivot. And then recursively apply the first part and the second part. So it's keeping doing the same thing over and over again until it's sorted. So let's look at, they should have the simulator for that. Okay. So yeah, when you start the program, we are assuming that the first element is the pivot. Now we try to, okay, let's read the begin. Divide the array into two parts so that all the elements in the first part are less than or equals to the pivot. And all the second part is going to be greater than. All right, we just select the pivot, right? 49, 42. So let's step. Oh, what did it just do? Let's start over again. We said pivot is 75. And then this is the 83. High is, we try to split them into low and high. So we just assume this is low for now and high is. We start to compare the low to the pivot. Then we know how to group them. So let's step. Looks like start from the high. Okay. So 86 is already higher than the pivot, right? So we don't have to do anything. Now we move it and we assume that this is another high, 36. Something has to happen here. There you go. It's just swap with a low. See that? Because 36 is less than the pivot. So it just take that value and swap out, right? Now let's look at, this is a new low, 36, 47. Alright, 47 is still less than the pivot. Let's see what happens. Then with increasing the low, right? So it's just working at the same time. Now it's increasing the low to the next low. I assume that 94 is a low. Now 47 is less than the pivot. So it should, right, swap 94 here and put 47 there, correct? Now we assume this is the next high, 64, but it's actually lower than the pivot, right? So what it's gonna do is also look at 47 is lower than, then it's moved to a new low, and now it's gonna see 64 is gonna swap with 92. Now we get a 78. 78. So let's look at the low. 64 is already low, then it should move, right? 43 is low, should move until it hit 93. And 78. Both of them are high, huh? So what does it do in this case? Both of them are high. Higher than the pivot. So it's moved it down because high is supposed to be on the right already, right? So 96 is high, it's going to keep moving. Now 35 is going to swap with the low, right? Because it's going to group the high, the right, low, and the left. Now swap. After swap, then it start to move down. 33 is low, it's going to move the low higher, right? $77 is high, it should be swapping with the high. There you go, right? And 42 low now is going to be moving low up, correct? Until it just meet each other. Now it's going to say, hey, I'm at the same location. This is where the pivot is going to go. You're going to move the pivot insert 75 between it, right? Now we start over again with the left and the right and do the same algorithm over again. Yeah, this is just show one move, right? Now you start to see if you keep doing this over and over again, the list is going to be sorted. Correct? This is called what? Quicksort. So how do you implement that? And what's the efficiency for that? Use an array. Right, this is an array already. And always assume that the first index is pivot. And then low is the next index. High is the max index. And then you have to iterate, right? Iterate and start to compare to the pivot. How many loops do we need? I think one is enough, huh? Right? So let's look at here. Now you understand the idea, right? And then it's called itself again. Like I said, it's going to do one loop. and then it's called itself again and again and again. Like in this case, look, we have Quicksort, and we do, this is the best case, right? If best case means when you stop the recursion. So same, we look at when the list dot length greater than 1, we stop the recursion. And then we might just try to iterate. This is just algorithms, right? To make sure all the list 1 less than the pivot or equals, and all the list 2 gonna be greater than the pivot. And then we do the same thing with list 1 and list 2 by call the Quicksort. So now let's look at how do we implement it. So we create a method called partition and pass list first and last. And this one returns a pivot index. In order to call the Quicksort again. Okay. Now let's look at partition. Right, the same thing. Like I said, you're gonna need one loop, right? For high greater than low, what's high? High is the index for backward search, right? We've seen that. Low is the index for forward search. Right, we're going to keep looping until they meet, then we stop the loop, right? And like I said, we assume that the first always going to be the pivot, right? Now we get a pivot. So we start to compare. While low less than equals to high, and this is just make sure that index still valid and the values less than the pivot. If it's in that case, we just increment the index, keep incrementing it, right? Same as the other way for high, we just keep decrement the high index, right? Now, if it happened to be high is greater than low, this is just try to swap the elements. When do we need to swap the element again? When we swap between low and high, right? We swap between low and high. So this is pretty much just, why is the if high greater than low? High is the index, right? So it's going to keep iterating. Index of high greater than low, we set the value of high put in temp, and then we can replace, this is swap between the values. When do we swap again? When the index, we look at index, or when do we swap? Are we looking at index high and low? Let's go back to simulator, right? So step. Right, when the value of high is lower than, we have to look at a pivot first, right? Not when the value of high is, if it's greater than the pivot, we don't swap. Look, right? We only swap when the value of high is lower than the pivot. So let's go back to the algorithms, out to the code. There you go. This one say while high is greater than low. Okay, we iterate through it until meet, right? Okay, this technically is just if. You just want to double check that you swap when they're not meeting yet. Because when you meet, you should stop. It's just checking, right? It's just double check. Because we've been do increment and decrement. So, and this is pretty much just try to swap. And this is where it start to look at high greater than first. This is start to decrement your high. Just like this. So this is just look at when the value is greater than equals to a pivot. You just keep reducing it. And the index still greater than the first index. Now this is when we start to swap according to values. If pivot greater than list high, right? Just like in this situation, pivot greater than high, right? That's why start to swap to the low. And this is where start to swap. Right, by moving the values to the first, which is the low, that's the low, and move pivot to the high. So else it's just return the first. If it's not greater than, you don't have to do swap. So it's going to keep repeating this. So what is the big O of this then? Of the partition? We know that when you do recursion call itself like this, it's going to be what? Do it over and over again. Do it over and again in a smaller version. Log n. Over again in smaller version. Now, how about this one partition? So if you look inside first, this is just big of 1, right? Sorry. This is just big of 1, correct? Constant time, because compare just ones. And this could be 1, 1, 1, it's just 4. So that's we call as 1, right? How about this? Is about what? The size of high. So we said high greater than low. And then this is also depending on the high. Low less than equals to high. This is like our card, the big O worksheet, right? Is it n or n square? So keep reducing high every time. This is just like n here, right? And this is on the other side, on the low part. This is like 2n, right? And we just keep doing that as long as it's high is greater than low. Now when you look at this, it's pretty much the same. High greater than low is like low less than equals to high. Is it another n or the same n? Is it n square n? Like this is 2n, right? But we have to evaluate like what this type of nested loop is. It depends on the condition here, right? That make n or n square. You should remember that, right? High greater than 0, I mean high is greater than low. We go look at, technically this one is pretty much the same as this one, right? Like, let's say 10 greater than 0 and 0 less than equals to 10. It's the same thing. It's just evaluating the value, pretty much. This one is just repeating itself, but itself is actually, it's just trying to look at the values. Make sure that it's still greater than pivot. So my question is, can we do just if here? If I don't do while, do you think if it's gonna work? No, because you have to keep reducing it. Because keep reduce over and over again to get to the location. Yeah. So what do you think? Is it n or n square? So let's look at how they evaluate. That one we already understand from simulator. So it said we talk about partition method that we just look at. Partition an array of n elements. It takes n comparisons and n moves. In the worst case, it's about n. For partition time. In the worst case, the pivot divides array each time into one big subarray with the other array empty. The size of the big subarray is one less than the one before divided. In that case, this will take about n square times. It's pretty much just your pivot accidentally gonna be 1, 2, 3, 4, 5 in that order. It's pretty much just if you try to do this in the sorted list, it's gonna be n square. Right? Because keep just pick the less. It's never pick like the one in the middle. If it pick the one in the middle, it's gonna be faster, becomes 2 and log n. It depends on the pivot values. So the worst case can be n square when you try to sort the sorted list with Quicksort. Any question on Quicksort? Heap sort. All right, so what's heap? So first you have to understand the concept of a binary tree. So what is a binary tree? So binary is stand for 2, right? So 2 that has 2, 3 that has 2 branches. This is a binary tree, right? It's always going to be, this is called root, and this is called children. We have left and right. It's always only limited by 2. You can see that. Okay. And this is a type of the structure that in the circle here we can store the values of the element. Now we're going to say we're going to put this tree to store. This is a full binary tree. Full means each node has 2 child or 2 children. What time is supposed to be done? 40. Okay. So each node gonna have 2 children, right? And you see they all have 2 children, right? Now we also have the word complete. So this is called full, right? This is called complete. So you look at the shapes. Complete means you're always going to fill in the left, but you can leave the right empty, the right bottom corner. So full is going to be pretty much a complete triangle shape if you draw a triangle around the dot, right? But complete is the triangle almost complete. But the only elements that are empty always at the bottom right corner. Like if I eliminating H and I, this is also a binary tree, right? But it's not full and it's not complete. If I remove these 2 nodes out, okay, H and I, make sense? So now you understand the property of the binary tree and how it looks, right? Now come back to heap sort. The shape of the binary heap must be complete. Okay? So a binary heap is pretty much just a binary tree that has a complete shape. Make sense? So binary heap based on 2 properties. One is the shape property has to be complete binary tree. And the second property is each node is greater than or equals to any of its children. Let's look at it. So this is called root, the first node. Always having values greater than its children. See that? And this is pretty much just the parent of another 2 children, and the value is always greater than. That's pretty much a binary heap tree or binary heap. So these are all heaps, but is D is a heap? No, because the tree is not complete, right? No, we're missing this guy. I mean at the bottom right, that you can miss one. This is complete. You cannot miss 42 and 14. Make sense? Complete is going to be this shape. Let's review again. You see that? You can miss this M, N, O, but you cannot miss G, C, you cannot miss them. Like complete means this is level 0, right? A must have 2 kids, right? Like if you're missing C, you don't have 2 children. That is not a binary tree because it had to be 2. Make sense? So this is not complete. This is not a heap. This is not a heap, binary heap. Okay? And this is not a heap. This is a heap. A, B are the heaps. C, D are not. Make sense? Now you understand what is binary heap based on the complete shape and the heap property of the parents always greater than its children, right? The values, right, of the parents always greater than its children. So one thing that you want to make sure that someone may confusing heap with something else, because in computer science they use heap in many terms, but now in this sort, heap sort mean a binary heap that we just mentioned. So now let's look at, if you understand the heap itself is already sorted. Is that true? Because the root always greater than, the parents always have the values greater than the children. It's already sorted. That's true, right? The thing is, you have to understand operations. So when I said the operation mean, let's say we have this is a data structure. We have an empty heap. We have unsorted number. We could put this unsorted into the heap. When you put, it has to find the right location for it. For example, let's do the Heap Simulator. Let's just use the one. Alright, enter a key to insert. Let's say I'm going to create a list. Let's make this list an unsorted list. 5, and then 3, and then 4, and then 2, and then 1. So this is unsorted, right? I happen to be, let's just do something like this. Okay, 5, 3, 1, 4, 2. So enter key 5. The first dot is always going to be 5 as a parent. And now I'm going to need to enter another key, which is what? Let's look at my list again. 3, right? I just going to do it in this order, right? 3, because this is unsorted list. It's going to go to the left because the shape, remember, it could not go to the right. If it's going to the right, it's not a full binary tree, right? Always insert to the left first. This is to a heap, correct? And now I'm going to insert another one. it's going to go to the bottom right here, because it has to be lower than 5. Make sense? And it has to be full or complete, right? See that? Now when I insert 4, where would it go? It should replace 3 and it should push 3 down. Why? Because if I insert after 3, it will give me the shape that is correct. It's always going to insert right there to the left of number 3, right? In order to keep the shape property, correct? But it has to swap the values between 3 and 5, I mean 3 and 4, in order to keep the value property, right? Because the parent has to be higher than the children, right? So let's look. So I'm going to insert 4. See that? It's going to swap and push 4 up. Any questions? Now when I insert 2, where would it go? Right there. And still keep the shape and keep the values property. So we got a heap. Now the question is, if this is insert to the heap, right? I could this is called max heap. Max heap means the parents always higher than, right, or the heap that the property values, right? The value is always higher than the children's. So if I start to remove, it's going to take form, you see, remove the root. Always remove from the root. Meaning the list is going to be sorted right away after I remove. Correct? Remove 5. I wrote down. Okay, so 5. And I just push it, right? You see that 4 has to go up. So if I remove 4, I just push it right to the right when I remove. To remove always, the root is always going to be 3. I remove 3 again. So it's going to be like that. And 2 has to go up. I remove 2 again. Now I have 1. And then I remove 1. What do I get after I create a heap and remove it? I get a sorted list. And this is called a heap sort. Use a heap to create the heap from the unordered list, right? And then remove all the heap values. Then you get the sorted values. Now, efficiency of this is depend on the algorithm on how to create and to remove the heap, right? And the algorithm is going to give you log-n. Why? Because the binary tree always give you log-n, which we will learn why binary tree give you log-n. Okay, and the sense is always go to first, like left and right, always in half and half and half and half. When you search, you actually search to the left half or right half. It's just like you divide in 2 every time. So that's why it's log-n. Okay, so heap sort is going to give you a log-n, and next time we're just going to come back and look at how we implement the heap here, and then we're going to look at analyze the efficiency wise log-n and log-n. Okay, so we can stop on the page 878 here, and we come back and look at heap class.